Hey everybody, welcome to tutorial number 9 in the Cilk Plus tutorials. Today we're going to be looking at the merge routine in parallel. Last video I did the merge sort algorithm, but we still used a serial merge routine even though we were splitting up the work in parallel. If you haven't already, try to grab a copy of Introduction to Algorithms 3rd edition, written by these guys. I found this version online, so it shouldn't be too difficult, although I could just post the link in the description afterwards. But yeah, so just open it up, and if you have the electronic version, go over to page 797 and basically just read this entire section. Try to make sense of it because they do use some pretty horrible variable names. So give it a nice read. It's going to give you the pseudocode. You're going to have to implement binary search. It gives you the merge routine in parallel. See over here, we're doing the spawn and the sync. For us, it's going to be Cilk spawn, Cilk sync. It's going to analyze it using the master theorem and different um, recurrences. It's going to tell you about the bottleneck that I mentioned in the previous video. It's going to give you the merge sort, the new merge sort routine, which is basically the same as the old merge sort routine, except we're just doing a little bit of an extra check, and we're actually passing it a temporary array to put both of the sorted subarrays in. So that makes it a little bit different than what we did last video, but it's not that hard to change the old code in the new code. Despite that, I'm still gonna be posting up the new code. But yeah, let's go ahead and dive right into it. So what we have here is basically the same file from the old video, except what we're doing is we're creating another list. We're creating a sorted list, and we're just setting everything to 0. We're still creating our unsorted list and setting everything to random values. But when we call the parallel merge sort, we're going to pass it the unsorted list, the bounds of the unsorted list, and then we're going to give it our empty sorted list and the starting index of that sorted list, so that once this is done running, sorted list is going to contain our sorted values, and list is still going to contain our unsorted values. So at the end, we're still going to want to free both lists, but before we do that, we're going to verify that what our output was actually sorted. So basically the same main method that as our previous tutorial. There's the same verify method, nothing changed there. Um, Regular merge sort and regular merge, both still the same. Here's an implementation of binary search. I did make use of the max routine in algorithm, so you're going to want to include algorithm just to find the max of 2 values. But this is basic binary search. You're searching for a key in a given list with left and right indexes. So nothing too complicated, nothing too new there. So parallel merge sort. So we got the unsorted list, start and the end, and the sorted list, start sorted. So we're right off the top, we're doing pretty much the same stuff that we did in regular merge sort, finding out the size, checking the size for the base case, and then otherwise we're going to be making our temporary sorted list. We're going to find our midpoint. We're going to find the length of the right-hand side. Also, we're going to be splitting up the work, so we're going to be sending it the left-hand side for this call and then the right-hand side for this call, and then we're going to sync them up and merge them. So basically the same as the other parallel merge sort, or the other merge sort rather. Just doing a little bit of extra stuff for the left and right-hand side of this temp array. We're going to merge these two. We're going to merge these two sorted subarrays, which is stored in temp, together into sorted, and then we're going to clear off our allocated memory so that we don't have any memory leaks, and that's pretty much it. So yeah, like I said before, don't be too reliant on these results because this computer that I'm running on right now is on its way out the door. So the parallel implementation is actually performing much, much worse than expected. Um, it should be worse, but it shouldn't be this much worse. And I'm pretty much blaming the fact that I'm using this computer. I'm sure that if I was using the computer I was using before in the previous videos, these results would be much, much better. Um, but yeah, this does give you, however, a good idea of the amount of overhead that you get when you try to split your work up into too many pieces when you don't have as many cores as you should. Um, if you had a GPU with like hundreds of processors on it, then that would be perfectly fine. But the fact that this laptop only has 4 cores, it's still an Intel processor, but it's still it's got 4 cores, 8 threads. They're all being used with this code, so there's nothing wrong with the parallel code or anything that I'm using here. It's just the fact that this machine is a little bit outdated. But the fact that this processor is going through so many context switches between the different tasks that it needs to do, it's basically the one thing that's holding this algorithm back. If we had enough cores to handle all that work, then this algorithm would be much, much faster. Um, Another thing that you could do is you can, oops, sorry. Another thing you could do is specify a threshold so that if you threshold, I don't know, 1,000 or 10,000, something like that, and you could check against this threshold. And the more runs you do against this, you can tweak your threshold based on your own computer and your own specs and to determine the best threshold to use. But basically, you check against this threshold, and if your unsorted list is, you know, smaller than the threshold, then you can switch to a different algorithm that could be faster for all these small base cases. So you only have to do the parallel stuff and split the work up into chunks that are small enough that you can handle them much more efficiently in a different algorithm. So like you could do a hybrid approach where you can do insertion sort on the rest of the items, or you can do quick sort on the rest of the items, or instead of continuing to Cilk spawn and Cilk sync, you can do the non-parallel merge sort instead of Cilk spawn and Cilk sync all the time. Um, but that's just a thought. The fact that we're actually passing extra parameters might make that difficult to, because if you were to check against the threshold in here and found out that this list is small enough to do the regular merge sort, you might have to do a little bit of extra work to make sure that all the right stuff is in the right list when you pass it there. And then once you pass it here, you don't have an output sorted list than that this one does. So you're gonna have to change main a little bit if you're gonna do that. But then again, I'm just giving you some advice. You can do it however you want, but that's probably the way that I would do it. But yeah, so I'm gonna post this file up. Um, it runs on this crappy computer, so I'm pretty sure it'll run a little bit better on your computer. But again, don't be too optimistic about the results for the parallel implementation because of the massive amount of parallel bottleneck that we're getting. If you were to, um, like in my previous video, I mentioned how a Cilk for loop that even though it implements Cilk spawn and Cilk sync, it actually performs better than Cilk spawn and Cilk sync because it's splitting up the work in half and it's only doing half of the Cilk spawn calls than it would be if you had it in a regular loop. Now, in merge sort, even though we are splitting up the work and we're still splitting up the work when we're merging, um, the fact that we're doing so many Cilk spawn and Cilk sync calls, we're doing one spawn and sync call every single time these methods are called. Whereas if you were to do, like if this silk spawn and silk sync was wrapped in a for loop, then this spawn would be called every iteration of that for loop. But like I mentioned before, the silk for loop, it actually does half the amount, or it only, it splits it down based on a grain size. And then you can also specify the grain size yourself, and that could help you tweak it up that way. But like I don't think there's a way, or at least a simple way, to change these from silk spawn silk sync into a silk for. Um, and that's why I told you about the threshold thing, because that would be like our user defined grain size, but for this algorithm. Anyways, yeah, enough rambling on. I'm gonna leave the video alone now, and we'll move on to the next thing, which is gonna be the flight data. So stay tuned for that for video 10. Thanks.